Hello. In this lecture, we are going to look at some aspect of the JVM and try to understand a bit more about what it's involved to have our Java code running in the JVM, so Java virtual machine. We are going to start looking at the Jvm architecture. Then we'll look at the Java just-in-time compiler, and in the end, try to answer the question if Java is compiled or interpreted. Which you might be surprised with the answer for this question. Jvm architecture. So Java is compounded by 9 components, and we will look at a bit about each one. So we're starting from the class loader. So class loader is the subsystem responsible to load our programs classes into the memory RAM for the execution. So, and then that's include the classes from our program itself, and that would care to load Java core libraries as well, and if you code require those. So it basically loads our class files and makes sure all required dependencies are available to be loaded as well. So this subsystem is also responsible to validate the code and checking if final methods classes are not overridden. So methods respect access control keywords. Variables are initialized before assigned, and so on. So it will do the full check about your code. So basically what our IDE already do, but Java would have to validate those as well, and that process is done on the class loader subsystem. So JVM has 5 different memory areas, where each area is used to store different information. So starting from the method area, it's where the JVM store classes structure, like metadata and code for methods and so on. So before it was used to be called perm gem, but since Java 8 it is called metadata memory. So perm gene used to be required to set the memory size, but this new native memory region now it grows automatically by default. And it's important to say that this memory space is separated from the program memory consumption. So that means that out of memory errors that we used to have is not going to happen anymore, because this new metadata memory area is going to be part of the outside of the program, and would consume the memory from our operation system. So we don't need to worry about that anymore. So let's talk a little bit about the heap memory. And actually then our next lecture, we're going to be talking only about the heap memory. More than that, we'll be looking at some tools to evaluate the memory in real time. And so, because that are going to be very, very briefly here on that explanation, especially because that's the memory area that most of developers know already. So very briefly, heap memory, it's where it is stored all the Java objects, right? And it's important to mention as well that this memory is shared across multiple threads. So that's why when you're writing multi-threading programs, it requires extra attention to race condition, and it's very important to have that in mind, that this area is shared across threads. And so more about that in a separate session. We are going to be talking about concurrency and multi-threading later. So for now, just keep in mind that this is a shared area, and it's where we store objects. And later we're going to be talking more about going more deeper on this memory. So for example, it's inside this area you have different let's say areas inside this one. So young generation, old generation, and so on. So stay tuned, because we're going to be talking more about this memory area later. And so moving on to the stack memory area. So it's another one that developers know already. So be also brief here. So, but basically the stack area, it's where contains primitive values and references to objects that are in the heap. Each thread has its own JVM stack, therefore it's thread safe, that area. And basically variable inside the stack exists only as long as the method that created them is still running. So it's every method created on a stack memory area, and when the method finish, that area, it's deleted. So don't have even action of the garbage collection. Garbage collection is another thing that we're going to be speaking later. So next memory area is PC registers. And PC registers will contain instructions of what you already have been executed and what it's going to execute, right? So that's basically keep the tracking execution plan for our programs. And the next one, native method, it works basically the same, but but it's more focused on instruction from the libraries in native part of the Java, so that it's kept in different parts. So something that I forgot to mention is that the PC registers would keep instructions separated by threads. So each thread would contain our own instruction or track of instruction that is going to be running or what was already executed. That's it for the JVM memory scheme. So we went through a little bit about some of the memory areas. Next lecture, we're going to talk more about the heap itself. But for now, that's it. So we're going to move to the execution engine. So the actual execution of the bytecode occur here on the execution engine. So execution engine executes the instruction in the bytecode line by line by reading the data that comes from the memory areas that we just looked at. So the execution engine has two important processes to execute the instructions. So one is the interpreter, and the other is the JIT compiler, so just-in-time compiler. The interpreter interprets the bytecode and executes the instruction one by one. Interpret the segment line is quicker, but execute this interpreted code, it is quite slow. The just-in-time compiler, in the other hand, takes more time to compile, but the execution is faster. So for a code segment that executes just once, it is better to interpret it instead of compiling. But when one method is called multiple times, having the instruction compiled to native code will speed things up. Can you spot the execution engine dilemma? If the JVM just interpret the bytecode line and execute the instruction, it will be faster because the process of compiling to native code will take time and slow down the instruction execution. However, if that instruction is executed many times, it is faster to compile before execute because the execution of a compiled instruction is faster, and once compiled, it will not need to compile the same instruction line again because it will retrieve the native code from the cache. To solve this dilemma, the execution engine internally checks the frequency of each method calls and decides to compile each segment only when the selected method has occurred more than a certain level of times. This is known as adaptive compiling, and it was brought by the introduction of the Oracle hotspot VMs. And that is why you might have heard the term warm-up, the JVM. Because it is during this warm-up that the metrics is collected and the adaptive compiler is put in place. So when you asked if Java is interpreted or compiled, now you know what to say, right? It is both. So the JVM will be compiling some certain part of the instruction, and it will be interpreted in the others, depending on the execution profiling. So the JVM is smart enough to decide when to compile or not a certain segment or certain instruction.